You abruptly awake as your eyes fly open. It is a sunny day, the UV rays of the sun beaming through your window, its warmth cast upon your face, when suddenly your gaze falls upon one of the most beautiful natural phenomena, a rainbow. The mathematical idea deeply rooted in what makes this display of colour possible is refraction, which is defined as the bending of light as it passes from one medium into another. The existence of lenses, magnifying glasses, and prisms are all applicable examples of refraction, which all play significant roles in our lives, even if the significance is often not appreciated, as without it we would be unable to see, as the convex lens in our eye converges the light onto our retina via refraction. The mathematical formula deeply intertwined within the concept of refraction is Snell's law, which was pioneered by Willebrord Snell in 1621. Snell's law describes the relationship between the angle of incidence, θ1, and the angle of refraction, θ2, with respect to the normal as light travels from one medium to another, with n1 and n2 described as the refractive index of the two mediums. We can use Snell's law to explore how rainbows form in nature and calculate the angle of refraction. In this example, the circle represents a water droplet, and the medium outside the area is air. The white dotted line perpendicular to the tangent plane is defined as the normal. The sun's ray is represented by the red line, which refracts upon entry, reflects inside the droplet, and then refracts once more. The dispersion of the light accumulates with other water droplets, creating a visible spectrum of light and color across the sky. The refractive index is defined as a ratio of the velocity in a medium versus the speed of light in a vacuum. The refractive index of air, n1, is 1, and the refractive index of water, n2, is 1.33, derived from the white light's average behavior. For a rainbow to occur, the elevation of the sun, θ1, must be less than or equal to 45 degrees. In this example, the angle of incidence is defined as 42 degrees. With these variables now defined, we can now use them to calculate the angle of refraction, θ2. We will need to algebraically rearrange the Snell's law formula to solve for θ2. First, we will divide both sides by n2, then we will take the sine inverse of both sides, which cancels out the sine on the right-hand side, isolating θ2. This gives our expression for solving θ2. Now, by substituting in values we have previously defined, we can calculate the value of θ2, which is found to be 30.14 degrees, which is our angle for refraction in the water droplet. The mathematics of refraction is further relevant and vital to our society, as it allows us to connect and network with others with fiber optic cables, as their low refractive index cladding material and high refractive index core creates a prime environment that causes the light to continuously reflect, which is called total internal refraction. Fiber optics are used for long-distance and high-performance data networking, as well as internet, telecommunication, and television, which is a large part of our modern identities and desire as humans to communicate with others. Refraction is also found in solar panels, where the mirrors and lenses reflect and refract sunlight onto collectors, where it is transformed into thermal energy. Refraction assisting our responsibility to use cleaner energy sources in our action against climate change. We need to appreciate mathematics more and realize its importance to our society, to be curious about the mathematics behind our existence and the constant hidden formulas behind every aspect of our lives, and to ultimately strive for enlightenment.